All right, let's get started then. So welcome to week 9, so AI504. And this week we're going to talk about word embedding. So before we get into the world of NLP, the first thing to learn is word embedding. And then RNN will follow, then transformer, then BERT and GPT and all that kind of stuff will follow. So there's not a lot to cover today, so hopefully we can end a bit earlier than usual. So the contents are word embedding, document embedding, then contextualized word embedding, which will just. All right, I'm going to have to mute everybody. Right, so word embedding and document embedding, then contextualized word embedding. This will be just a small, a sneak peek, because we're going to have to learn. We're going to be learning this in BERT in full detail. Then subword encoding, which will be probably the main content of today. So let's start with word embedding. Document embedding, this will be just a one slide or 2 slide thing. So no need to worry about learning it in too many details. All right, so word embedding. So what is a word embedding? So I'm pretty sure a lot of you have already heard what word embedding is. Basically, embedding is basically just, learning a lower dimensional space representation. We call that lower embedding. We call that embedding. And word embedding is basically learning the representation vector of a word, right? Expressing a word as a vector, that's basically what word embedding is. And before even neural network came along, people already have been using a vector representation, vector form of words to do NLP. NLP has been around for like at least 50 or 60 years. NLP is a very, very long, it has a very long history. So vectorizing a word or vectorizing a document that kind of idea has been around I don't know, probably more than 30 years or so. So vector form of word is a pretty familiar concept, but in neural network, the era of deep learning, we have cranked it up a notch, so to speak. So we have a new, we've learned how to embed a word in a more expressive manner. But before that, we can learn a more classical way to vectorize a word or document. So before we begin, so basic concept. What is a word embedding? Like what kind of desirable property do we want out of word embedding? So for example, cat and a kitty are similar words, so they should have a similar vector representation. So, but compared to hamburger, which is a completely different word than cat or kitty, in a semantic manner. Semantically, cat and kitty are pretty close, and hamburger and cat should be far away apart from each other. So we want the kind of things to be reflected in the word representation of cat and kitty and hamburger. So a cat vector and a kitty vector should be close to each other, but a cat vector and a hamburger vector should be far away from each other. So we want that kind of stuff to happen. So how can we encode a word, which word is a discrete concept, right? Like from A to, if you think about all the words in the English dictionary from A to Z, a boy, cat, girl, dog, whatever, all the way to Z to zebra. There should be like 50 or 60,000 words, or maybe 100,000 words in an English dictionary. So, and they're all discrete, unlike a height or weight. It's a discrete concept. So what do you do when you want to vectorize a discrete concept? For example, if you want to vectorize a blood type, there is A, B, if we forget about the minus and the plus, there's A and B and A, B, and O. So there are 4 blood types. So if you have 4 discrete concepts, 4 categorical variables, basically, then how can we vectorize them? We can do it like this. Typically, we can use something called one-hot vector. So A can be 1, 0, 0, 0. B can be 0, 1, 0, 0. AB can be 0, 0, 1, 0. O can be 0, 0, 0, 1. So because there are 4 words, 4 concepts in the entire set, so there's the size of the vocabulary is 4. So we need a 4-dimensional vector. 1, 2, 3, 4. We need a 4-dimensional vector, and each dimension will represent a single concept. So the first dimension represents A. Second dimension represents B, third AB, fourth O. So exactly the same thing. If we have, for example, if we have 50,000 words in a English dictionary, then there should be a 50,000 dimensional vector. We can prepare a 50,000 dimensional vector, and the first word, so the first dimension should represent the first word in English dictionary, which should be A, and the last word in the last dimension should represent the last word in the English dictionary, which should be like ZZZ or something. So just an example. Let's say that there are only so many words in English dictionary. What's the dimension here? It's like 20 or something, right? So, and we happen to use the fifth dimension as a representation of horse, and fourth from the back to represent the word zebra. So this can be a typical example of a one-hot representation of two words, horse and a zebra. The problem is that even though the word horse and the word zebra are semantically close to each other because they're both horses, right? So we want them to be close to each other, like how we wanted cat and kitty to be close to each other, but hamburger and kitty should be far away from each other. Just like that, we want horse and zebra to have some kind of similarity even in its vectorial form. But the problem is, if we represent words as a one-hot vector, then there is no similarity or whatsoever, because if you calculate the inner product between the two, so the inner product between horse and zebra is what? Is 0. If you just multiply this, if you multiply every single dimension and then sum it all up, it'll be just simply 0. And the Euclidean distance between them is, if you calculate them, it'll be 0, Euclidean distance between horse and zebra would be 2. Well, actually, we can forget about the upper 2. Then it's square root of 2, right? And this is not just this is not just between a horse and a zebra. Between every single word, it'll always be the same. Because if you use a one-hot vector, then any pair of words will have an inner product score of 0, if you think about it, and the L2 distance, the Euclidean distance between any pair of words, will always be square root of 2. So that basically fails the desirable property that we want out of vector form of words, which is that semantically close words should be close to each other, and semantically irrelevant words should be far away from each other. But this is not observed when you use one-hot vectors, because this is always the same. Any word pair will have an inner product score of 0. Any word pair will have a Euclidean distance of square root 2. So it doesn't just, it just completely fails the objective, right? Right. So yeah, exactly like here. So one-hot vector cannot reflect the desired property of word vectors. And that's so far with the one-hot vector, the one-hot representation of words, and document representation, which is, or sentence representation. Actually, it could be sentence representation, paragraph representation, document representation, anything that is beyond a single word. They should also have a vector representation, right? When you want to do like a sentence classification, whether a sentence is a positive sentence or a negative sentence, we need a sentence representation, which is a vector form of a sentence, in order to classify. If you want to classify a document's category, like whether it's a sports article, whether it's a politics article, whether it's a science article, when you want to categorize a document, you need a vector representation of a document. So we run into the same problem. But instead of using a one-hot vector, just like in the word representation, in sentence or paragraph or document representation, we have a counting vector. So just like this. So there's sentence here. Actually, no, there's one document, document 1, document 2, and it's a very short document. So document 1 is like this: John likes movies, Mary likes movie, Mary likes too, and document 2 is John also likes football. So we're going to construct a set of vocabulary to represent these two documents, which are these. So there's John likes movies, also football, Mary too. All this is the entire vocabulary to that are used in the entire two documents. And then what we can do is we can count the number of times each word is occurring in each document. So for document 1, John occurs once, but likes occurs twice because there's likes and there's likes. Movies once, Mary once, 2 once. In document 2, we have John once, likes once, also once, and football once. So all in all, this will be a vector representation of document 1. 1, 2, 1, 0, 0, 1, 1. So 1, 2, 1, 0, 0, 1, 1. This is the vector representation of dot 1. And 1, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0 is the vector representation of dot 2. So this is a little bit better than, one-hot representation. So the problem with one-hot representation of a word is that any pair of words will give you exact same inner product and exact same Euclidean distance. But here, if we start counting and then using the counting vector as a document representation or sentence representation for that matter, it'll give you a more informed, it gives you more information. Basically, if you do an inner product between the two, or inner product between the two, or Euclidean distance, L2 distance between the two, it is more informative because as you can see here, these two documents, document 1 and document 2, have a pretty like a large number of overlapping words. It overlaps. John overlaps, likes overlaps. Actually, only two. So John overlaps, likes overlaps. So if you do an inner product, at least it won't be 0 anymore. And if you do a Euclidean distance, it'll be some number. But if you imagine another document like document number 3, doc 3 equals. Let me see. So. Mary, let me see. Yeah, we need to add. Let's assume that there's another word. Mary hates football. Mary hates football. Let's assume this is dot 3. Then the vector representation of dot 3 would be like 0, 0, 0, 0, 1, 1, 0. Let's assume that there's hate here, so we need one more dimension. 0 for hate, 0 for hate, 1 for hate. So if you think about this dot 3, then the distance between, then the inner product between dot 1 and dot 3. So dot 1 and dot 1, inner product dot 3 would be what? Would be 0 because there's no overlapping word whatsoever between the two documents. So you immediately have a concept of similar documents and irrelevant documents if you use counting vector as a document representation, because the inner product between dot 1 and dot 2 is non-zero, but inner product between dot 1 and dot 3 is 0. So that kind of reflects that how relevant and irrelevant two documents are. Dot 1 and dot 2 are more relevant than dot 1 and dot 3 are, like that, right? So this is a little bit better than word one-hot representation of a word vector. Right. So, and then comes some other ways to represent like documents. There, if you think about, if you're familiar with topic modeling, like LDA or Dirichlet district, like what was that? So, hierarchical Dirichlet distribution, Dirichlet process, or Chinese restaurant process, or Indian buffet restaurant process, that kind of stuff. Like topic modeling has been a big thing for at least like 5 to 10 years in the late 2000s to early 2010, maybe. So probabilistic topic modeling or matrix factorization, similar stuff. So you can, as you've seen here, you can represent a document and a word. You can represent the document as a word count. So this is what we call a term document matrix. This is what we call term document matrix. You have one axis. In one axis, you have all the terms. Another axis, you have all the documents, and then each cell occupied is the number of times the in a specific word or specific term occurs in a specific document, right? So we have a term document matrix. And using that, you can do a matrix factorization to get a lower rank representation of the document, or you can do a probabilistic topping modeling, So you can do a SVD on top of this, or you can do like a probabilistic SVD on top of this as well, which leads to probabilistic topping modeling. And yeah, that was big hit, as I said, like in the 2005, maybe starting from 2005 to maybe like early 2010, 2011, 2012, something like that. Right, so that's the classical, I wouldn't say, like, topping modeling is a bit modern, but anything before that, like a word, one-hot representation of a word, or word counting, term document matrix, those are all classical ways to represent a word or document. And this is a very, very typical, very, 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 very traditional method used in NLP or text mining or information retrieval or search engines. And then came distributed vector representations in 2013 by Thomas Mikolov, which is word2vec. So we're going to talk about word2vec now. So word2vec is, well, before word2vec, so what distributed vector representation? So let's talk about what this is. The distributed vector representation is a antithesis, is like in contrast to one-hot representation, which is out of all the dimensions, out of all the 0 dimensions, only one dimension is 1 and all the other dimensions are 0. That was one-hot representation, right? So in contrast to that, distributed vector representation of a word is where your word vector or word embedding is like this, like 0.1, negative 1.2, 3.5, negative 3.2, something like this. Basically, your word representation consists of continuous float value, basically. So it's not a discrete, integer values anymore. So that's what we call a distributed vector representation. And even before word2vec, like in the middle of 2000s or something like that, there were some other studies that propose how to train or how to learn a distributed vector representation of words, but they were not a very big hit because word2vec has a very, very peculiar characteristic that really, attracted the attention of NLP researchers. So we're going to talk about that. So the good thing about having a good distributed vector representation, or I'm going to call this a continuous representation of word vector, is you no longer have a fixed inner product between all pair of words. You no longer have fixed Euclidean distance between all pair of words, which was the case for one-hot representation, where all Euclidean distance was always square root of 2. All inner product between any pair of words was always 0. So in contrast to that, if you have this kind of representation, continuous value, then you won't have that kind of problem anymore. But only as long as you have a good representation of words. So word2vec does that, actually. Word2vec exactly does that. So it's an algorithm. Word2vec is an algorithm for training a vector representation, of a word from context words. So we're going to get to this. So you have a bunch of corpus. You have a bunch of words. A bunch of actually, you need a document. You need like a bunch of documents to train using word2vec. You need like a Wikipedia or book corpus or tweets or blogs or news articles, something like that. And from those corpus, from those bunch of documents, using word2vec, you can derive a fixed vector representation of a word in a continuous form, in a distributed manner. In a distributed form. So the good thing about having a continuous representation as opposed to one-hot representation is depicted right here. So if you want to depict a cat, if you want to describe a cat in a vector form using a one-hot vector, then this is a typical example. But if you have a continuous representation, you have this. So what is the good thing and what's the pros and cons of having this kind of representation of a cat? So first of all, good thing is that when you have a one-hot representation, then if you change, for example, if you change this value to 1 and this value to 0, then it'll immediately be a different meaning. It'll immediately represent a completely different object, different meaning. Like it'll be like a dog or like a truck or a car or something that's completely irrelevant to a cat. So the essence is that when you have one-hot vector like this and you meddle with, when you modify the contents of the vector, then it'll immediately change the meaning of the vector. But when you have a continuous vector like this, then slightly modifying the value wouldn't really change the semantic of the word, of the vector. For example, if you change this to 35.2 or 45.5, does it really change the meaning of change the meaning as drastically as changing this to 1 and changing this to 0? Probably no, right? Probably no. So that is the like the pro strength of a continuous representation of a word, which is robustness. Like slightly changing the value wouldn't really change the meaning of the word, as opposed to one-hot vector. But the problem is that then there is no fixed meaning at all, because like 93.2, 93.21, 93.19, they're all cat. They're all cat. So, but here in the one-hot representation, only 0.000000010 is cat, and all the other is not cat. So that's the drawback or weakness of distributed representation, which is that the meaning is now a bit fuzzy. That is why actually the word is fuzzy as opposed to crystal clear cat here. The word cat is a little bit opaque. So that's the pros and cons. So hope you guys can understand. But the good thing is, as I said, since you have a continuous representation, you can now calculate. You can now have a meaningful Euclidean distance. You can now have a meaningful inner product between any word pair. So that's that is like one of the strongest properties of having a distributed representation. And as I said, in order to do so, you need a good representation, and Word2Vec happens to give you a good representation of words, good distributed representation of words. So how does it work? So, well, actually, we're gonna skip this. And so a couple of examples. If you guys are interested, if you're curious about distributed word representation before Word2Vec, there were a couple. So there was 1 and 2. So if you guys are interested in this, you can actually look it up. So Word2Vec is the most representative example of distributed representation of words. So desirable property. So the very, very interesting property of Word2Vec is once you learn a vector representation of words, you can do interesting things. You can do actually an interesting linear operation using the words. So here, this is the most popular, most important, famous example, which is this. So once you derive a queen vector, so vector representation of a word queen, and king vector, which is the vector representation of the word king, so it's a king embedding. So once you have queen vector, king vector, one vector, man vector, you can do a very interesting operation like this. So queen minus king and a woman minus man, they're approximately the same, which means that the vector representation of words understands the relationship between the words. King and a queen and a king is this is like a man, and this is a woman and a man. Woman and a man, and also happens to be the same as what else? Like vector of actress minus vector of actor, and almost equals vector of aunt, 고모죠, 뭐 고모, 숙모, minus vector uncle. Like they're all approximately, I mean, they're not exactly the same, but they're approximately the same. Which means that just by simply training the word vectors, it automatically captures the relationship, the semantic meaning or semantic relationship between words, which is a phenomenal example. I mean, which is a very, very interesting phenomenon. Because so I'm going to show you how you can train Word2Vec here. So the training process of Word2Vec is extremely easy, but then the end product is extremely useful. So that is why it became so popular in 2013, when nobody imagined this kind of thing could be possible. And then came after Professor Kyung-Yeon Cho's Seek to Seek sequence-to-sequence models, and then the attention came in 2014 as well, and then came all the follow-up work of NLP. Before that, in 2012 came AlexNet, and then 2013, 2014, like ResNet came, InceptionNet came, and then people already knew deep learning was the way to go in computer visions and image processing, but people had a bit of a doubt when it came to NLP and the language. Like they didn't really know if deep learning would be applicable to language, because language is not because computer vision deals with pixel values, right? So pixel values are natural signals. Like audio was also like one of the domains that early adopted deep learning, because audio signals, the pitch and the amplitude and the frequency, they're also natural signals. So it was quite it was quite a natural fit. But language is not a natural signal. Language is a tool, or it's an information developed by people. So it's a kind of an artificial signal, and people really didn't expect deep learning to really shine in deep learning. But then Word2Vec showed that it could work, and then came sequence to sequence, then came attention, then way back in the way into the future in 2018, BERT came out. So then people knew that deep learning was the way to go. Anyway, so that was a side story. So like this kind of thing is possible using Word2Vec. So basically, what this means is that this kind of thing is happening in the latent space, in the vector space of the Word2Vec. So there's like, if you think this is the origin, so this is y-axis, this is the y-axis, and then actually let me just erase all this. This is your y-axis, and this is your x-axis, and let's assume this is the point of origin. Then this would be your men vector. This would be your woman vector, like here. And this is your king vector. This is your queen vector. So each word occupies a different position in the latent space, but their relationship, so queen minus king, woman minus men, have the same meaning, because it knows the relationship between the words. So that is why you can do this kind of thing. Yeah. And if you actually move it over here, then it would be queen minus king, queen minus king plus men would be woman, something like that. Some interesting operations can be done with Word2Vec vectors. Some examples here. So the real examples. So I think this is a two-dimensional representation of. So Word2Vec, when you use Word2Vec, you need to specify which dimension you want to learn the word embeddings into. So typically, back in the day, people use like 100 or 200. They didn't use 120 or 256. They use like 100 or 200 or 50, something like that, some arbitrary values. But in order to actually visualize, you need to further compress it into two-dimensional space. So I think the original author of Word2Vec used PCA to visualize. So you can see the real examples here. So you can see that this is men versus woman relationship. There's niece, nephew, sister, brother, aunt, uncle, and that kind of stuff. Woman, man, and you can see their difference, the difference vector between any pair of female word and male word is approximately the same. It's always this, like this. They're not exactly the same, but they're usually the same. And then company and CEO. So I think this is the company side, and this is the CEO side. You can see the same thing happening here. Can you just give me a minute? I'm sorry. Actually, just give me a minute. All right, sorry for the delay. Yeah, call came. All right, so we were seeing the company CEO example, and next one is city zip code. So zip code is 우편번호죠. City, so all the different cities in the United States and the different zip codes, and you can see all again, like the representation. I mean, the difference factors are almost the same. One more example, comparative and superlative. 그러니까 이제 비교형이랑 이제 그 뭐라 그러죠? 그 최고형이라고 그러던가. 네, 하여튼 뭐 이제 그런 거죠. So slow, slower, slowest, short, shorter, shortest. So again, like very, very similar difference vectors between different words and different examples. And this is not just applicable in English. Actually, it works in any language. So there's I'm not sure if this link still works, but it used to. You used to be able to do an example like this, like test it out, like 한국 마이너스 서울 이제 플러스 도쿄 오면은 일본이 나오는 이제 그런. 그러니까 이거는 뭐예요? 이거는 이제 그 나라와 수도를 이제 서로 관계를 보여주는 거죠. 이제 어떻게 하면 되는 거죠? 한국 빼기 서울은 일본 빼기 도쿄랑 같으니까 이제 그거를 이렇게 다시 이 항을 이렇게 항을 옮겨주면 도쿄 항을 이제 옮겨주면은 오른쪽 일본이 나오겠죠. Right. So the one thing to actually note is that if you do this, it doesn't automatically give you, for example, like here. So when you this you can actually see. So this is a vector. The vector minus vector is a vector, right? And this is another vector, and you can see how similar how two different vectors are using inner product or Euclidean distance. But when you see an example like the queen, let me see. What example would it be here? A queen minus a woman. Let me see. A queen, according to this equation, queen minus woman plus man equals king. No. So if you move it over here, and then if you take it over here, and if you take this one here, then you will get this equation. So when you have a queen vector minus woman vector plus man vector, then this is also some vector. This will be some vector, right? This will be some vector, but this vector wouldn't exactly be king vector. So when people show this kind of example to you, this doesn't mean that this vector is exactly the same as king vector. It means that so first of all, when you do an operation, these minus and plus operation, you will get a vector, and then you can, out of all the words starting from A to all the way to Z, you will have different vectors, right? There will be all different vectors. And then out of all the vectors, you calculate which one is the closest to this vector that you got from this operations. And then this vector happens to be the closest in terms of Euclidean distance, closest to the king vector somewhere here, king vector. Like this happens to be the closest to this. So that's why people say this equals to king, but doesn't mean that this operation gives you exactly the king vector. As I said here, nothing is exactly the same anymore. So hope you understand that. So when you have 한국 minus 서울 plus Tokyo, then you will get a vector, and then that vector happens to be the closest to the 일본 vector in terms of Euclidean distance, or cosine similarity for that matter. All right, some more examples here. So these are pretty fun examples to look at. So author of this is called, I actually borrowed it from another researcher, Won-jae Kim, who is now a researcher in Naver, actually. So this came out probably, I don't know, like maybe 5 to 6 years, maybe 7 years ago, 2015, 2014, probably. And you can see that it works pretty well. So Barack Obama minus United States plus Russia gives you what? Gives you a Russian president, which is Vladimir Putin. Barack Obama negative minus United States plus Star Wars then gives you a president of the Star Wars, which interestingly is Anakin Skywalker. Yeah. So you can see what kind of knowledge is embedded in Word2Vec if you do this kind of stuff. What else? Like iPhone minus the cell phone, and then plus laptop is iPad, which is exactly, well, not exactly true because it should be MacBook instead of iPad, but still close enough. And interesting stuff, 소녀시대 minus 소녀 plus 아줌마 gives you IU, which is weird because IU should be younger than 소녀시대, right? If I'm correct. Right. So interesting stuff. Yeah, some interesting stuff was here. Yeah. Yeah, computer minus machine plus person, human, gives you 운영체제, operating system. So you can see what kind of things are embedded in, not, so you note that this whole thing was learned from, I'm not sure where Mr. Wonji Kim actually trained this Word2Vec from, probably Wikipedia, Korean Wikipedia or something. So you can see that what kind of knowledge is embedded in the Korean Wikipedia when you look at this or this, like this. So it's a reflection of human, like Korean people's knowledge or Korean people's belief, actually. All right, so how does it work? How does Word2Vec train or derive, how does Word2Vec give you a good representation of words? So the essential philosophy, the core philosophy is this: you shall know a word by the company keeps. It means that a word's meaning, semantic meaning, is determined by its neighboring words. So neighboring words, meaning the word that is right next to each other, right next to the target word, right? So yeah, here, distributional hypothesis, the meaning of a cat. So we want to learn a representation of cat, a word embedding or vector representation of a cat. And how do we learn it? How do we train, how to derive a specific continuous valued number for cat vector? And the meaning of cat is captured by the probability distribution of PW cat, PW being the words around the cat. So cat is usually, cat should co-occur with what? Should co-occur with pet or what? Or food or her or cute or dog, like these are the words that typically co-occur with cat, right? So you can see that the meaning of the cat should be somewhat relevant to the meaning of pet, meaning of food, meaning of purr, meaning of cute, and meaning of dog, and something like that. So that is the basic philosophy right here. So there are two implementations of Word2Vec. Actually, Word2Vec is has two forms. One is the CBO, which is continuous bag of words, and one other is skipgram. And people use skipgram more often than CBO because it shows better linear operate this kind of stuff. This kind of operation is more neatly done using skipgram rather than CBO. So the philosophy of CBO is that there's a target word, which is the word cat. We want to learn a representation of the cat word cat. And the cat's identity is determined by what? Determined by the sum of its neighbors. So there's neighboring word, there's two steps to the left, one step to the left, one step to the right, two steps to the right. So there are four neighboring words, and their neighboring words vector form. So there's neighbor words vector, neighbor word vector, neighbor word, and then you sum it up, and then you want this summation to be predictive of the cat word, which is our interest, the word of interest. So that is CBO, and skipgram is the other way around. It's the opposite. When you have a word cat, and so when you have a cat vector, you want your cat vector to be predictive of its neighboring words. So there's no summation. Here's the summation part, but here in skipgram, there's a summation. So you have simply your target word cat being trying to predict its neighbors. Two to the left, one to the left, one to the right, two to the right. And so, as I said, skipgram is more frequently used. So how to train Word2Vec? You first need to set a window size. So window size being how far to the left and right you want to go in order to. So this definition of your neighbor. So in here, the window size was 2. Window size was 2. Here, the window size is 3. And using skipgram, what you want to do is you select the target word, which is one in the center, and then you want to predict all the words in your neighbors according to your window size. So here, you want to predict 3 words to the left and 3 words to the right. And CBO is the other way around. CBO is that when you have window size 3, you want to sum these 6 words all together, and then you want that to predict your red word, which is the target word. But as I said, skipgram is more often used. So what do I mean by predictive? It means that when you have using skipgram, when you have a target word, you have a target word vector, and then you use that word vector to maximize the softmax score between this word and this word, between this word and this word, between this word and this word, this and this, this and this, this and this. So that is how we call it being predictive, as opposed to some word that is not in this window. Like, for example, if this is a cat, and then this is like, let me see. So I have a cat as a pet, like this. So this is a complete word. So I have a cat as a pet, and then you want your cat vector to be predictive of a, of have, of I, of as, of a, and of pet. But there should be some other word somewhere, some other sentence, like, there should be like I don't know, a car is used for transportation, something like this, basically, And you can see that, so cat should be predictive of these neighboring words, but not with completely different sentence here, because this sentence is not within the context, not within the neighbor. So anything outside the neighbor scope should be not predictive of, but anything that is inside the neighbor, inside the context, should be the red word, the target word, should be predictive of. So that's the difference. So anything that is within context, it should have some meaning. It should be predictive of. Anything that is outside the context, it should not be predictive of. So that is basically how Word2Vec is trained. So exactly like this. So there's a let me see. So this is a target word. Actually, is it? I think, yeah, this, okay, so this is a target word. So VC is a target word, and then this is your neighbor, and this is your neighbor, and this is anything that is outside the neighbor, basically. So you can think of it like this. And you do it for all words in your context. So you have the log function here, which is here. So you have log function, which is basically a softmax between word and target word and its neighbor, normalized by all the words in the entire vocabulary, in the entire English dictionary. So that is a softmax. So you have a softmax, log of softmax here, and then you do it for all the words inside your context, inside your neighbor. So it's minus m to n. When your m is so in this case your m was 3 in this case, and then you do it for all sentences, or all documents or whatever, right? So that is basically it. So it's a very, very simple training procedure. You have a bunch of documents, or a bunch of sentences, actually. You have a bunch of sentences, and then you set a context window within a sentence, and then you slide that window. So you start, for example, let me see. I have a cat, and actually I'm running out of space. So let me see. I have a cat, and you have a dog. So let's assume that this is our given sentence, and let's assume that your context window size is 2. Then what you do is you start with this window here. So this is your target word, and you have two context. You have 2 in the left and 2 on the right. So 2 in the left, 2 on the right. You calculate a softmax score between these two. I'm sorry, this two, and this two, and then you update your word vector parameters, and then you move on to the next context window. And now your cat is a target word. So you will have softmax score between cat A, cat have, cat and then cat U, and then you move on again. Then next time you move on to the next sliding window, and so on and so forth. Basically, that's it. That is the entire thing. And as you and when you backprop, you want to maximize this, which you want to maximize the softmax score, which is meaning that you want your target word to be predictive of its neighbors. You want to maximize, and as you maximize, you backpropagate and you update your word vectors, because they're all because they're all vectors. This is a vector, this is a vector. So every word, your target word, your context word is all vectors. So that's it. And then you just keep doing it for your fixed number of epochs, and that's it. So pretty simple, right? So basically, you're just telling your word vectors to be representative or to be predictive of your neighboring words, and that's it. And then somehow it can do weird things like this. Very interesting thing. Very interesting properties arise from very simple training procedure. That is why Word2Vec was such a big hit in 2013, 2014. Right, yeah, the training details there's a bit of a more detail in training procedure actually. So when you train, there's a reason that your target vector is called V and your context vector or neighbor vector is called U. Is because your target the vector that you use to represent the target, which is the one in the center, and the vector and the parameters or the vector embedding, lookup embedding that you use for your neighbors, which are I, have, cat, and, are different in the original Word2Vec. Word2Vec uses two sets of vectors, two sets of lookup embeddings, which is one used for target, one used for context embedding, meaning one used for the neighbors. So there's like a lookup embedding for target, lookup embedding for the neighbors. And the reason for that is because the author thought that they should serve different purposes. When a word is used for a target and when a word is used for as a neighbor, they should serve different purposes. So that is why the original author used two different vector lookup embeddings for two different lookup embeddings with W1 and W2. So they call it input vector and output vector, which is basically saying that target and a neighbor. But actually, if you train Word2Vec using just one lookup embedding, it still works pretty well. So it's just, like a technical detail. Yeah, some more technical details. So if you look at the one here, which is when you want to calculate the softmax probability to maximize you want to maximize the log of softmax probability when you train Word2Vec, right? So when you want to maximize this entire thing. So this involves softmax, and this involves the sum of this, exponentiated inner product between words, which is sum. So all words, all vocabulary in all words in your entire English dictionary should go through this summation. So that takes a long time and whenever every single shift from here to the next window to next window to next window to next window, you always have to calculate this entire sum over your English dictionary, which takes a long time. So people didn't like that. So softmax information being slow. So they actually came up with something called hierarchical softmax, which I'm not going to go into. If you're interested, you can look it up. It's basically using a binary tree, using a binary tree form of softmax to accelerate the speed optimization process. Another is using negative sampling, which is I don't want to go over the entire sum. I just want to sample maybe 5 or 10 words out of the English dictionary, and then I'm going to be done with it. So that's negative sampling. Negative sampling is used pretty heavily these days as well. So as I said, instead of going through the entire dictionary, you sample a fixed number of samples from your English dictionary, and then basically an approximation. So people use this. Well, I mean, people don't use Word2Vec anymore, but if you wanted to use Word2Vec, you should probably use negative sampling. Right. So that's the technical details. So application of Word2Vec. So what do you do so after you've learned Word2Vec, what do you use it? What do you use it for? Like, is it just for doing some funny stuff like queen minus king equals man minus woman? Actually, that is not true. There's a bit of more use to Word2Vec. So once you have trained Word2Vec, you have a fixed word vectors for each word in your English dictionary. So you can actually use them as you can load their weights when you're training like more downstream applications. So you can use them as an initialization. For example, word similarity is one very simple, straightforward application, but using machine translation or part of speech tagging, named entity recognition, sentiment classification, clustering, semantic lexicon building, or basically anything, basically any application, downstream application of NLP, you can use word vectors to initialize the lookup embedding, because any of these, any downstream task of NLP usually involves word embeddings, right? You need like word representation to derive a document representation, something like that. So you can, whenever your downstream NLP application involves a word embedding, you can use word-to-vec embeddings as an initialization. And sometimes it helps, sometimes it doesn't. It depends on the application, depends on the task. But some tasks, for example, like like similar sentence similarity estimation, those kind of tasks will be very, very it'll benefit a lot from word-to-vec vectors. But some other applications, probably not. Right, so that was word-to-vec. And then glove is another version of famous version, another popular variant of word embedding learning algorithm. So word-to-vec came first, and then glove came. So word-to-vec has a bit of a drawback, which is that it takes a long time to train, because you need to slide your context window along a sentence, and then you need to do it for all the sentence. So it takes a long time to do a for loop. And because of that, researchers in Stanford came up with another algorithm, which is called glove, which is based on the term document matrix. You remember the term document matrix, right? There's like a term axis here and the document axis here, and then each cell was occupied by the number of times each term occurs in the document, right? So using a term document frequency matrix, you can do a bit of like a very clever trick to do a similar training procedure as word-to-vec, semantically similar training procedure as word-to-vec, but you don't have to slide the window, because you have the entire global view of all the words and how many times they occur in each document. You have a global view, so that is why it's called glove, because it uses a global view to derive a vector representation of each word. And it follows this, but we won't go into the detail. And then doc2vec it's like an extension of word2vec, which is you not only want to learn the word representation, but you want to also learn document representation. And in order to do so, let's say that you have some number of documents in your repository. Like this is doc1, this is doc2, doc3, doc4, doc5. So and you assign one vector for each document. So this is document 1's vector, this is document 2's vector, this is doc3's vector, doc4 vector, doc5 vector. And then you use that when you train word2vec, basically. So this is actually here it's using paragraph ID, but this can be a document ID as well. So you have a sentence that occurs in the document. So since this sentence occurs in this document. So what you do is when you train word2vec, you also alongside training the word2vec, you slide in, you add one more embedding, which represents a document, not a word, which represents a document, and then you slide it in alongside the word representation learning procedure using exactly the same word2vec principle. This is SIBO, and this is the what was that? Skipgram. Right, exactly like this. So then once you've finished your training, then you will have a document representation vector as well as word representation vectors. And then you can use those document representation vectors to do like document clustering or search engine or document classification or that kind of stuff. So it's a straightforward extension of word2vec. But these days people don't use doc2vec, or people don't use word2vec or doc2vec, any of them. People just use BERT now. So, and BERT is a very flexible architecture. It will give you a word representation, but it'll also give you a document representation. It will give you a sentence representation. It'll give you a paragraph representation, anything you want. So, which we will cover maybe 2 or 3 courses, 3 lectures after. Right. So far, any question? Word2vec and glove and doc2vec. As I said, people no longer use word2vec or glove or doc2vec, but this is such a seminal work. This is like the history of NLP. Like this all sparked the whole notion of word embedding, sentence embedding, representation learning, and that kind of stuff. So that word embedding was the beginning of all that. So you should really keep this in mind. Right. If there's no question, we'll move on to subword encoding. So far, everything was based on words. We saw the term document matrix, term document frequency matrix, which is based on words. We were learning word embeddings. Everything was based on words. But now, these days, people don't use words anymore. People use something called subword encoding. So what is that? So large IT companies like Google, which have a lot of NLP, which have a lot of interest in NLP because Google is based on search engines. So they provide their service to all language in the entire world. So concept of word is very inflexible. It's very strict for companies like Google, which needs to service all different kinds of, it needs to have a multilingual service. So they want more flexible unit other than words. And because words, if you base your service based on words, then new words always come along, like new words like this, good vibes, or like I don't care, I'm for you, something is like something. Like new words always are introduced in like language evolves over time. So if you base everything if you base every single service based on words, then your service will be out of date pretty soon, especially ever fast changing world we live in. And similar words like Christopher in English is Christoph in, I think this is Polish. So there's similar words represented in a slightly different manner in different languages. And because new words were actually typos or very shortened abbreviated form in twitters, like tweets. These are all cause of headaches for companies like Google. So they want more flexible, more smaller size unit, smaller than words. So that is why they came up with something called subword. Before we get into subword, you can naturally think of a simpler solution, which is based on character. So if word level is not flexible enough for you, then you can actually go down to the character level. You can just say, cat can be broken down into C-A-T, boy can be broken down into B-O-Y. So in the entire world, if you think about the number of alphabets, English has 26 alphabets, and all the Latin-based language, German, Italian, Spanish, French, they all have similar alphabet set. And if you think about the number of alphabets in the entire world, it won't go over 300 or 5, probably not more than 1,000. If you think about all the different language and different units of word, actually, except for Chinese, because Chinese has thousands and thousands of characters. But besides that, if you think about typical languages, then if you have character level models, then it'll be way more flexible, because all the new words, all the typos, all the Twitter words, all the abbreviations, they can still be broken down into characters. So if your model is based on characters, your model will be very, very flexible. But the problem is that if you break down your language if you break down everything into a character level, then it'll be too long, if you think about breaking this down into characters, then there's how many? This will be 30 or 30 something characters. If you think about breaking down this entire thing into character level, this will be hundreds and 200s or 300s. I'm not sure, hundreds. So typical sentence will be broken down into hundreds for thousands character level sequence, and your model will not be able to handle that amount of long sequences. So that's the problem with character level models. But it does perform pretty well, in the mid 2010s, 2016, their character level models did show promising results. So word level translation model and character level translation model had a similar performance. So as long as you had a very big VRAMs, and which can take all the long sequences derived from character level broken sentence, it could work pretty well in theory. But as I said, not is just the sequence will be too long. So these are the details of how you can break down the sentence into a character level like this. Like even the spaces and everything is just character level. So because of that, pros and cons of the character level model, people have came up with two more trends, which is actually this is right here. We use something called word pieces. So word piece or sentence piece or byte pair encoding, these are the representative examples of subword encoding methods. So people actually are using this very, very heavily these days. Hybrid models, not so much. Hybrid models, some models, some words are represented as words, some are represented characters, and that's hybrid. But actually, subword encoding can actually subsume, like it's a superset of this kind of approach. So all the BERTs and GPTs and all that kind of stuff is based on subword encoding these days. So subword encoding is the way to go, especially. Nobody uses word embedding anymore, actually, unless you're very, very interested in word embedding. So as I said, word piece is something developed by, I think it was developed by people in Google, and then word piece was further extended to sentence pieces. So word piece / sentence piece is like one of the representative methods to do subword encoding, but byte pair encoding is a bit more straightforward. So we're going to look into that. So it's byte pair encoding is originally a compression algorithm. So compression meaning that you have you need to send a message over like a transmission server or whatever. Like you need to send a signal, and then when you want to send the signal, you want to compress them so that you don't waste your resources. So this is all coming from Shannon's information theory. So originally, byte pair encoding was used as a compression algorithm, and it's replaced. You can actually we can read this paper to see where it actually came from. So it's a very, very simple algorithm. So what we want to do is you want to come up with an embedding unit which is smaller than words but larger than character. Right. So, for example, ideally, what you want to do is, for example, if you have a word like concentrate. Let me see. What's a good example? Like displacement. Displacement. If you have a word like displacement, the word level approach is that treating displacement as a single word. So that's word level. This is word level. Character level would be D, I, S, P, so on and so forth until N and T. Then we need something called subword level, which is smaller than word but larger than character. And hopefully we want this to be broken down into some meaningful units like this, place, month, right? If you have a word unit like this, subword unit like this, then you can actually reuse these components for other words as well. For example, like element. If you have a word element, if you have a word like element, you can break this down into ele and month. So you can use the same month here and here as well. So if you can break down your words, your vocab, your text into a meaningful, smaller subword unit, then it'll be very, very informative. So you want this kind of things to happen. So how do we do it? Using byte pair encoding. So it's a bottom-up clustering approach, and you start with character level. So you start with unigram vocabulary, meaning A, B, C, D, E, F, G, all the way to Z, and then you take most frequent n-gram pairs to form a new word. So there's an example here. So let's assume that you have you counted, so you have a document, and then out of all the documents, you counted the number of words, and how many words each time, how many times each word occurs in your entire document. So happens to be low occurs 5 times, lower occurs 2 times, newest occurs 6 times, and widest occurs 3 times. So this is your word frequency list. And using this, what you do is you start with the only the characters. So out of all this, you have L, you have O, W, E, R, N, S, T, W, I, D. Yeah, exactly that. So you have this. You have this. And then what you do is, this is your starting. So this is your vocabulary now. This is your dictionary now, with all the characters occupying your vocabulary, occupying your dictionary. But then what you do is you count the number of times 2 grams, how many times each 2 gram occurs. So you count LO occurs 5 times here, OW occurs 5 times here, LO occurs 2 times here, OW 2 times, WE, ER. You count this the number of times each 2 gram occurs in your entire dictionary. And it happens to be ES occurs the most 9 times, because it's 6 plus 2, compared to LO, which occurs 5 plus 2, which is 7 times. Compared to that, ES occurs 9 times. So ES becomes your new vocabulary, new word in your dictionary. So that's how you start. You one at a time, you add new subword into your dictionary. So you started with ES. Now ES is now a single. Now, even though ES is a two character word, now you can assume this is a single character, and single character meaning that next time EST becomes the most frequent word, because ES is now a single character. So ES plus T occurs 6 times here. ES plus T occurs 3 times here again. So it's 9 times. So EST becomes your most frequent word to add, most frequent 2 gram to add into your dictionary. So EST is added. Next time is LO's turn now, because you no longer have something that occurs 9 times anymore. So you move on to the next most frequently occurring 2 gram, which happens to be LO. So LO 7 times. So LO is added here. And you would do it over and over again. You keep running this for loop until you're satisfied with the number of words that occupy your dictionary. So LO, and then then probably is after LO it'll be LOW, and then after that it'll be what? It'll be I don't see a good candidate. Anyway, you keep doing this. And as you do this, you can see that informative subwords are added to your dictionary, because EST is like, they're usually used as like a superlative, like newest, widest. So EST is a very useful subword, and short length words like low, boy, cat, dog, girl, like those will also be added in the dictionary eventually. So it'll be only the long words like displacement, elementary, or something like that. They will be broken down into subword units. So you keep running this, and then how many times do you run? Like how many for loops? How many times do you want to run your for loops? It depends on your preference. So you need to prefix the size of your dictionary. You want your dictionary to be, so I'm gonna run byte pair encoding with dictionary size target of 30,000 or 50,000 or 100,000 or 10,000. Depends on your preference. So you need to predefine the size of your dictionary, and then you run your for loop until you reach your dictionary size. So that's byte pair encoding. It's pretty easy, right? So yeah, you have a target vocabulary size, and then you stop when you reach. So whenever you stop whenever your dictionary is the size of your preferred target. So it's a deterministic longest piece segmentation of words. So once you've learned your dictionary, once you've learned your vocabulary, whenever your words come in, like whenever your like newest comes in, you can immediately break it down into N, E, W, EST, like this, because EST is the longest one in here. So you take EST from here, you break it down, and then NEW. There's no NEW anything anywhere here. So you take the NE and W here. So that's how this will be broken down in the downstream task, in the downstream application. Right. So the good thing about the byte pair encoding is that it automatically decides the vocab for system. So you don't need to think about you don't need to think about what kind of words you're going to use for your vocabulary, what kind of filters you're going to use, you don't need to care about any of that. You just run byte pair encoding for the fixed number of vocab English dictionary size, and then it is just done. You automatically have a dictionary to use for any of your downstream tasks. So it's a purely data-driven vocabulary construction algorithm. Very, very powerful, very, very easy, very, very, convenient. And you don't even have to know the language. You can just take Japanese, Korean, Indian, whatever language you want to have your service for. You can just take a bunch of documents in that language, like Polish Wikipedia, Korean Wikipedia, Japanese Wikipedia, whatever. You just have some bunch of corpus. You run your byte pair encoding algorithm, and then for a fixed number of times, and then you have a dictionary to go. So very, very powerful system, and something that companies like larger IT companies like Google or Facebook or Amazon or Netflix would very, very like, if you think about it. Right, then there are some other variations like word piece and sentence piece, but the only difference is that byte pair encoding only cares about the frequency. Like it only chooses the most frequent n-grams all the time. But in a word piece and sentence piece, instead of choosing the most frequent n-gram, they choose the n-gram that minimizes the perplexity of the language model. So so they want, anytime you want to add one more word in your dictionary, sentence piece, word piece, it chooses the word that maximizes the language model log likelihood. So it's more information theory driven, basically. But basically, it's the same, and it doesn't really give you a lot of benefit, because GPT-3 is based on byte pair encoding. So, and it works like a charm. So it doesn't really matter. Right. So yeah, if you're interested in word piece and sentence piece, you can go to this website, or you can read the paper and see how the principle it was based on. But as I said, byte pair encoding works like a charm, and people don't even use like characters anymore. They use actually the Unicode bytes, like UTF-8 or Unicode byte pair. They actually use the bytes because they want to incorporate like emoticon, like emojis and emoticons, and like all the different kinds of like symbols and that kind of stuff. So so people don't want to just people just don't want to play with like characters, like Latin character. You want to incorporate anything that is inside human language or language in the internet. So they actually use Unicode byte pairs. Right, some examples in word piece and sentence piece, but we can just, like Hypatia can be broken down into this. So H, sharp YP. Sharp means that there's something before this word. So again, sharp ATI means that there's some other subword before this, which are this sharp A, something like this. So, but H doesn't have sharp, which means that H is the start of a new word. So that's how word piece and sentence piece, indicates a start of a word and the intermediate subword in a word. Right, so that was the subword encoding. So please you need to be very, very familiar with the subword encoding, because we're going to learn BERT and GPT like two or three lectures after. So, and as I said, BERT is based on word piece or customized word. Yeah, BERT uses a variant of the word piece. So you should be very, very familiar with the word piece model, or at least the concept of subword encoding. Right, the final thing is something called embedding, contextualized word embedding. So 이제 한국말로 하면 이제 문맥을 반영하는 word embedding인데, 그러니까 이제 word to vec에 있는 word embedding과는 좀 다르죠. So this is in contrast to word embedding that you learn from word to vec, there's something called contextualized word embedding. So we'll see what it is. Just a couple slides. So in word to vec, what you do is you train, based on a bunch of documents, you train a fixed word representation, a fixed vector for each word in your entire English dictionary. So for example, if you want to retrieve a word for boy, if you want to retrieve a vector for boy, then you can look it up, and then you can have a boy vector, which will be some number. If you have cat, you can have girl. Like any word, you can directly retrieve a fixed valued vector That is what word2vec does for you. But consider this scenario. So hey Elmo. So Elmo is some language model, some NLP model, Or actually, it's a word embedding model. So hey Elmo, what's the embedding of the word stick? And if you think about word2vec, you can just immediately look up the word2vec embedding, lookup embedding table, and then just retrieve the stick vector. But here, this Elmo is a contextualized word embedding model, because so it instead of directly retrieving a fixed embedding of the word stick, it asks there are multiple possible embeddings. So use it in a sentence, because stick can be used as like an actual stick. 그러니까 막대기에 스틱일 수도 있고, 아니면 이제 or you stick to something like sticky, you know. So being attached to something. 그러니까 이제 끈적끈적 이렇게 딱 달라붙는다 할 때 스틱도 있고. 그래서 스틱이라는 단어가 여러 의미가 있기 때문에 이걸 그냥 스틱의 단어 벡터를 줘봐라고 하는 게 아니라 이제 그 문장에서 써가지고 어떤 의미로 쓰는지 알려달라는 거예요, 이제 이 모델이. 그래서 얘가 이제 okay, so here let's stick to improvisation in this skit. So which means that you stick means 그러니까 여기서 이제 우리 이번 즉흥 연주에서는 우리 이번 그 뭐 스킷에서는 즉흥 연주로 이제 유지합시다. stick to라는 게 이제 어떤 그 유지한다는 거니까 이제 그 계획을 바꾸지 않고 원래대로 간다는 거잖아요. 이제 그런 의미의 스틱이다라고 이제 문장에서 보여주는 거죠. So the user is actually using the word stick in a sentence to specify which semantic meaning of stick the user wants out of and correspondingly the word vector that represents this stick. So in that case, Elmo the model retrieves a corresponding, semantically accurate word embedding of stick. So this is as opposed to word2vec, because word2vec doesn't really understand context, because word2vec will give you only one word embedding for the stick, and that stick should be used for any generic purposes. You don't know what kind of meaning it captures. It could be stick for 막대기 스틱일 수도 있고, 이제 뭐 달라붙다 스틱일 수도 있고, 워드 임베딩에서는 뭐가 될지 알 수가 없는 거죠. 근데 이제 이런 식으로 이제 그 새로운 언어 모델인 이제 엘모 같은 거는 문장을 보고 그거에 해당하는 단어 벡터를 주기 때문에 훨씬 더 이제 의미가 풍부한 그런 단어 벡터를 줄 수가 있다. 그래서 이제 이게 의미가 있다라는 거죠. Right. So there are a couple of words, or contextualized word embedding models that can serve this kind of purpose. That asks, so where you give a sentence, and then where you give a sentence like let stick to yada yada yada, and then skip. So if you give this sentence into BERT, then BERT will give you a corresponding word vector for let's vector. There will be stick vector all the way to skip vector. So that is how BERT model can be seen as a like advanced word2vec. Like word2vec uses a fixed word embedding, but BERT uses a contextualized word embedding. You have to feed an entire sentence, and then the BERT will understand the sentence and then return a word embedding for each word in that sentence. Same for Elmo. So BERT uses transformer, Elmo uses LSTM. That's the only difference. And Elmo is the first contextualized word embedding model that claimed verify the importance of this kind of contextualized word embedding philosophy. But it used LSTM, like forward LSTM and the backward LSTM to embed the sentence and retrieve the word embeddings. But BERT uses transformers, so it's a bit better than LSTM. OpenAI's GPT is a bit different. It's a language model. It is mainly used for generating new words and generating new sentences, so it's a bit out of scope. But BERT and Elmo are kind of the same thing, right? So you can see the advantage, or how powerful BERT and Elmo models can be as opposed to word2vec. So as I said, word2vec, you can use word2vec pre-trained word embeddings from word2vec as an initialization for downstream tasks like machine translation or document classification or sentence similarity estimation. And as I said, that word2vec sometimes helps and sometimes don't. It's because word2vec's word embeddings are such a strict, like it's a very, very restricted, very inflexible word embeddings. But BERT in Elmo is a very flexible, very contextualized word embedding. So that is why BERT is used for every single downstream task in NLP. It could be used for question answering, could be used for document classification, it could be used for inference, like logical inference. It could be used for sentence similarity classification. Anything you can use BERT, because BERT is a very, very flexible contextualized word embedding model. And if you put some task-specific model on top of BERT, then you can think of BERT as like a word embedding model. Hopefully that gives you like a big picture of why BERT works so well as opposed to word2vec. Right, so this is it for today. So you can think of this as like a history class, but in the practice session this Thursday, you will be implementing word2vec, and then you will be actually training word2vec, and then actually do this linear operation, queen minus king equals like woman minus man. You're going to have a time to actually explore all the different interesting operations. So hopefully that'll give you a more in-depth understanding of word embeddings and subword embeddings and that kind of stuff. All right. Any question before I end the class today? Actually, I hope that we would end a bit earlier than usual, but then it's 12 o'clock again. So sorry about that. Question 22번 슬라이드면 한참 전인데. 이번 슬라이드 오토엔코더 형태의 네트워크 그림인데 이 그림 워트백과 무슨 상관이 있는가요? So you can think of this as this is a word like this is a one-hot word vector. So there's like so 1 to v. So there's like v. I'm gonna have to erase all this. In your English dictionary, there's v number of words. So like could be 2,000, 20,000, or 30,000, 50,000, and each dimension occupies a single word. So it could be a and boy all the way to like zzz, right? And your word representation will start as a one-hot embedding, one-hot representation vector, but then using a lookup embedding in word2vec, it'll be downsized into a n-dimensional vector. It could be like 100, it could be 200, it could be 300, it could be 256, anything you want, because when you train in word2vec, you need to specify the latent space, the size of the latent space for your word embeddings. So it's n size here. And if this was a boy, like 001, 00 all the way to 0, then it'll be mapped to a specific specific latent space, this like continuous valued representation in the lower dimensional space, in n-dimensional space. And then what you do is you want this to be closer to your neighboring words. So there's like a bunch of neighboring words like here, right? There's a bunch of neighboring words, and each neighboring word will be different as you slide along your sentence. That is why you have a different lookup table. As I said, originally in word2vec, there was a lookup table for target, lookup table for neighbor, right? So that is why you have different W prime for the neighboring vector. This is W for your target vector. Target word. This W prime for your neighboring words, and you want to have a certain inner product maximization between the two, because you can see here inside the exponentiation, there's an inner product between neighboring word and inner product between non-neighboring words. So for the neighboring words, you want to maximize your inner product. For the unneighboring words, you want to minimize the inner product. So that's why it is depicted like an autoencoder setting, but it's not exactly an autoencoder though. So hopefully that makes sense for you. Cool. All right. Right. So if there's no more question, I can end the class. If you do have questions, you can always use Classroom. And deadline for your project number 1 is this Thursday, if I remember correctly. Thursday, like 23:59 p.m. ish, right? So please submit something. It doesn't have to be a perfect FID score. As long as you submit a gradable results for both projects, you will still get a B- or B, or for that matter, So I think it was B- if I remember correctly. So just please you don't have to get a perfect score. Just at least submit something, according to the format. You have to respect the format. If you break the format, it doesn't grade, or it causes error for TA, you will get a 0 score anyway. So please very, very strongly respect the format the TA suggested. Is it Friday? I think it was Thursday, but I'm not sure. It's on the Classroom, so you can just look it up. I won't change the deadline anyway, so don't worry about that. All right, so I'll see you guys next Tuesday. I think it's the time for RNN next Tuesday, so it'll be a bit more relevant. So good luck with the projects, and then I'll see you guys next Tuesday. Bye-bye. Thank you very much. 네, 감사합니다. 네, 감사합니다.